speak about functions from the loop itself.
Thank you. And thank you for inviting me to speak at this wonderful institute. I think it's going to be a good series of conferences if you maintain. So I'm very happy to be here. Okay, so what I'm talking about is a project with some collaborators that I will name with. And the project has to do with computing functions, actual explicit functions. I won't show too many of them. I'll show how to obtain them. This project all starts from some conjecture that was made in 2019 by Rinat. We're trying to find cluster algebras that will help us sort of climb the mountains to proving the full conjecture. But in the meantime, this is about how we started.
Sorry, what's the conjecture? Who's conjecture?
I'll take the conjecture.
Oh, yeah.
Yeah. Okay, so let's start with something that I hope everyone here is very comfortable with, which is McDonald's eigenvalue equations. So we always use this as a sort of guide. So you have the McDonald operator, which is a q-difference operator in the variable x. So x here is a multivariable, s is a multivariable. I hope it's not confusing for people when I use this notation. S, okay, maybe you're not very happy with seeing a variable s instead of the highest weight lambda, but let's just keep it as s. So s is also a multivariable. This q-difference operator acts on s and spits out an eigenvalue, what we call an eigenvalue, which is the elementary symmetric function in S1 through Sn. Usually we identify S, so Si is t to the row I, the value vector, q to the lambda I, and then you're comfortable with writing down polynomials with highest weight lambda. But here I want to keep S as the formal variable, so it's not actually just these are not integers necessarily. And so if you write down such an equation, you can find a unique solution iteratively by solving this equation, by postulating where you want it to be solved as a series. And so you write down the series. It starts with a function which is symmetric in the variables x and s. Symmetric under the exchange of the variables. That is, if you write s as essentially q to the lambda, and x as essentially q to the mu, can you guys actually see the screen in the back?
If you flip the curtains to face the other way, it will be better.
Oh, there's also like a layer on the screen.
Yeah.
That makes sense.
No, you want the other one.
No.
The one with the B, the
Okay,
change.
the change.
But I think it's
The bigger part.
There.
Yeah.
Is that better?
There you see it.
Okay. Doesn't help the people in the back. Okay, so this function is symmetric under the exchange of these multi-sets of variables. And you look for a series solution in x to the power of negative roots with some coefficients, which can be functions of s, which start with 1. Then it has a unique solution because of the form of the McDonald difference. So this series is called a basic Cauchy-Strauss series or a universal series. I'll explain why it's called universal series. So if you pick an integer partition or a dominant integral weight and plug these values in for s. Yeah, so you evaluate s at t to the value vector q to the lambda, then he truncates these coefficients that you computed c of s, they truncate eventually. And this just becomes a polynomial. In fact, it's symmetric if you normalize it for symmetry. So it's called a universal series solution because you can get any normal polynomial by specializing. Okay, all right. And then before you plug in any special values, this series has certain dualities So there are two dualities that we use a lot. So there's bispectral duality, which means you can exchange the variables x and s. So McDonald in his book writes it down as you exchange lambda and mu, but you can actually just take x and s to be formal and just exchange all the x's and all the s's. And you have this symmetry modulo this function delta, which is this product over positive roots of some logarithms. And then there's something called Poincare duality, which exchanges t with q over t, which allows you to exchange some limits. So those are the two main dualities that we know are true for McDonald universal series. The bispectral duality means that I can take the McDonald eigenvalue equation and rewrite it and to get the Pierre rule from McDonald functions. That is, what happens to a McDonald function when I multiply it by any elementary symmetric function. And so there's some operator H, which is just a conjugation on the McDonald difference operator, only acting on the variables s this time. And so this looks almost like the eigenvalue equation, only this time HA is acting on is a q-difference operator in s. This is not how we usually read the Pierre rule, right? We don't read it as an eigenvalue equation, but you can read it as an eigenvalue equation with the eigenvalue, the elementary symmetric functions in use.
You're doing any finite type here?
No, I'm going to stick with type A, but such a statement is true for any finite.
Good source on this, I tried to make sure everything and stop mine, and it's very hard to follow.
Yeah.
Do you have a good source? I mean, did you write it down?
Oh.
Somebody write it down? What is this? This is the theoretical space.
We actually read Charlie.
Huh?
We actually read
You read
Charlie.
it.
Yeah.
Great.
Catch me here. There's a story behind this. Yeah. Yeah, so there is such a thing for any finite type. Maybe Stokman?
Yeah, so I'm going to paper in the
Yeah,
hands.
yeah.
Oh, yes.
Yeah. Yeah, okay, so this H is a q-difference operator in S. I'm not going to write it explicitly. I haven't written down any operators explicitly so far. And you can solve this equation as a series in S. Okay, this is the same function Pxs, which has a series solution in X to the minus positive roots. You can also solve it as a series in S to the positive roots. Those two things are equal up to whatever normalization factor. You know, I can multiply this function by any function of x, and it will still be an eigenfunction of h. H doesn't act on x. So I normalize it by the same function delta that's here. If I normalize it this way, then it's again q to the lambda mu, and then it starts with 1. Okay, so those are two different series solutions using bispectral duality. I'm not going to talk about the McDonald case in this today. What I'm going to say is that there is some limit of this. I want to talk about, this is a conference on cluster algebras. I want to explain where cluster algebras come in. They come in the q-Whittaker limit. So people usually call the q-Whittaker limit the limit of McDonald theory when t goes to 0, but you can also take t going to infinity because of Poincare duality. So that's actually simpler for me. So I'm just going to do that. And then I'm writing down explicitly two of the operators here. What happens in this limit when t goes to infinity, you have to renormalize a little bit. Nothing really happens to the McDonald operators. They look about as complicated. They're rational q-difference operators. But something drastic happens to H. You lose the symmetry. When you exchange x and s, you lose the symmetry. So I'm going to call this, let's say, the first Pierre operator, h1 of lambda. It just becomes a Laurent polynomial. It's not a rational function, it's much simpler. So this is what people usually call the Toda Hamiltonian quantum Toda Hamiltonian. quantum difference Toda Hamiltonian. And what I do here is I'm using two different quantum tori. Remember, D acts on S, H originally acted on S, I had to renormalize S. I'm taking the limit, not when S is finite, but when Q to the lambda is finite, so I have to multiply S by something. And so I have two different quantum tori. One of them is T sub X, the other one is T sub lambda, n-dimensional quantum tori. So I think we heard about it before. So H acts on T lambda and D acts on Tx. Any questions so far? Okay, so that's good. So yeah, usually people no longer call the difference operator in X a McDonald operator, so I don't know what the right word is, but it's some sort of Mercenar's operator. The language seems to change a lot, so I'll call the eigenvalue equation the Mercenar's equation, and its solutions, they're again series in X to the minus positive roots. And these are called q-Whittaker functions because they're eigenvalues of H1, which is the Toda equation. But for the McDonald operator, actually, you could just take the first McDonald operator. Its eigenvalue is the first elementary symmetric function in X. But when you take the limit when t goes to infinity or 0, the eigen values are no longer sufficient. There's a degeneracy. You actually have to take all n equations to solve for the function you need, because the eigenvalue becomes very simple. For example, the first Mercenar's operator has eigenvalue q to the lambda 1. So apart from the fact that you have to take all n Mercenar's equations, you can get a unique solution as a series in x to the minus positive roots. And if you solve, you get some coefficients that depend on lambda. And if you plug in dominant integral lambda, you'll get polynomials, symmetric polynomials. So those are what's called q-Whittaker polynomials in X. So the Toda equation, which is what I called the theory rule before, again, you just need the first one. Nothing happens to the eigenvalues because they're functions of X, and X is finite in the limit going to infinity. It's S which is not finite. It's S that causes this lack of symmetry. So the first theory rule is enough to solve this equation uniquely. I call it Q because it's normalized differently. The function delta simplified a little bit. There's no more T in the problem. And this is going to be a series in q to the lambda I plus 1 minus lambda I with the positive roots. Okay, so I have two types of series equations for these things, and they're both q-Whittaker functions. This function doesn't obviously simplify when I plug in dominant integral weights, but it has to. Okay, any questions?
So why is it called theory equation?
Because it's what happens when you add one more elementary symmetric function to the partition. I think that's what it means.
Okay. So that is traditionally what is called the theory rule.
Yeah.
Okay, so it's coming from that. I see.
So for me,
Yeah.
this is just the Toda equation
Okay.
in this thing. So there's something that some people call twist, or you can look at it as, so there's a spherical data in the McDonald theory. When you take the q-Whittaker limit, only part of it remains, not all the spherical data exactly. But there is this element which is usually called T, it is sub to Z, which acts on the spherical data, and it acts on my two difference operators. So the operator, I want to introduce this new operator G. G is acting on the quantum torus to T lambda. It's a q difference operator in lambda. It has a bunch of quantum logarithms. This is my definition of a quantum logarithm for today. It's all right. And then it has something, so the quantum logarithm, so phi of x commutes with x, but doesn't commute with t sub x, the q difference operator in x. So it doesn't commute in this way. And then gamma of t lambda, that's the q difference part of it. All I have to know about it is that it's adjoint action on t, commutes with t, and its adjoint action on q to the lambda translates q lambda. And you'll see me writing this this physics notation for let's say q by ordering in this case. So the only thing you have to know about this is that this order doesn't matter inside the dots. Okay. There is an explicit formula for this monomial transformation. So you can write it as an exponential of the log squared of t lambda over 2 log q. But really all you have to know is this adjoint action.
Please.
I know.
There's ventrostatic in it. You,
I will not use this T again.
oh, but
Yeah.
the things you're writing down, they don't have anything to do with that twist, do they?
What I want to say is that this operator acting on the quantum torus is going to be called an n-twist operator. I'll show you on what. In a second.
This operator.
This is an operator on some quantum torus, right? It acts by an adjoint action. And it acts on something. And let me show you what it acts on, right? Yes? This T I won't use again, but unfortunately I will introduce another T. I agree.
Don't understand. So the expression that you're writing,
I'm writing down an expression for what I'm going to say is something acting by an adjoint action on some variables.
but at the moment it's not acting anywhere. So what is capital T sub lambda?
This is the Q difference operator in the quantum torus T lambda. So it acts by adding 1 to lambda basically.
Ah.
So I think I introduced it before. Here. So T lambda multiplies Q to the lambda by Q to the delta IJs.
Ah.
So it's the Q difference operator. I have two quantum tori's here.
Oh, I see.
One of them is in X and the other one is in lambda.
In that.
It's the symmetry between X and S, which I lost a bit, but. Yeah, I should have made a more of a point about this. Okay, so. The thing about this is that this operator on the quantum torus, H also acts on the quantum torus, and these two operators commute. And because the eigenfunctions of H are uniquely determined up to scalar multiple, the eigenfunctions of H are eigenfunctions of G. And I can characterize these eigenfunctions as eigenfunctions of G. You can compute the eigenvalue, and it's the Gaussian in S. So this is the same gamma as before, if I wrote gamma of T. Now I'm writing gamma of S. This thing commutes with all xi, and then it doesn't commute with all txi. So this is in another quantum torus, tx quantum torus. So one thing you notice about this is it's a symmetric function. Okay, remember that the eigenfunctions of the eigenvalues of H were symmetric functions. If I had a spectral parameter, this would be the generating function for all symmetric functions, the exponential generating function for all these. But I'm not going to go there today. But it makes sense that the eigenvalue of G could be symmetric. Okay. So you can solve for eigenvalues, eigenfunctions of H, or you can solve for eigenfunctions of G, and it doesn't matter which we want to choose G. And again, I explained I want to choose. So I wrote before Q to the lambda dot mu, it's the same as writing X to the lambda in this case. So X to the lambda means X1 to the lambda 1, X2 to the lambda 2, and so on. And I look for series solutions. U to the minus lambda dot positive roots, they look like this. So it's a series solution. And I look for eigenfunctions that have eigenvalues, which is this Gaussian. The Gaussian is pure next word. Alternatively, I can look for eigenfunctions of, again, t, this time math cal t, which is just normalized so that it has eigenvalue 1. So it's just an adjoint action on G, but normalizes the eigenfunction of t, start with 1. With eigenvalue 1. Okay. We'll come back to this.
So, sorry.
Yes.
I mean, you wrote down what is gamma of x.
Yeah.
And previously you meant you wrote gamma of t lambda.
Yes.
Is it the same gamma?
It's the same gamma, you just plot t lambda I in here.
So first I didn't really define G, I didn't understand what gamma was.
So there is,
Ah,
there is an explicit
okay.
formula,
I didn't see.
but what matters is how it commutes with a quantum torus.
Let me see action of this involution in SL2.
The whole thing is the action, yeah. So this times the quantum logarithms. Let me see. So what is SL2C here? So this is called Toda quiver, and just ignore the coefficients for now. This is a quiver that you realize. So it's part of a big family of quivers that I used to call q-system quivers. But now I'm going to call it a Toda quiver in deference to my collaborators. You can realize this quiver by choosing cluster X variables in the language of Fock-Goncharov, given by the root data of the, so cluster X variables are given by the root data of the algebra. And you can see how you would generalize this to any simple root system. So I have a quantum torus T lambda. And out of this quantum torus, I make cluster X variables q to the lambda T lambda to the minus alpha A and q to the lambda dot alpha A. So I put the X primes on the lower row and the X on the upper row. And if you compute the Q commutation relations between these things, you'll get this quiver, I think. Or if you choose any other root system, you'll get some quiver. You can see how you get that. And then you can invert this somehow. And the cluster A variables, what Coleman and Zelevinsky like to use, that's given by the simple weights of Gitta. So here, for me, omega A is E1 plus dot 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 plus EA. Okay. So the cluster A variables here, again, are in the quantum torus T lambda. And the operator that I call the den twist realizes an action of the quiver automorphism. So this is just the principal part of the quiver. It goes like this. Mutate that all of these unprimed vertices, they commute with each, these mutations commute with each other. And then all the arrows will be reversed. So just exchange the primes with the non-primes. So just turn this upside down, and this is we're going to get the same quiver apart from the coefficients. Okay, and I claim that you saw G, it had a bunch of logarithms. It had to be some sort of mutation sequence, right? So this is the mutation sequence, I think. And I will not justify the name den twist today. But it's acting on the quantum torus T lambda. So for example, let me remind you that G, so the adjoint action of G on these variables. These variables don't have any T lambda, they just have a q to the lambda. So they commute with any function of lambda. But they don't commute with T lambda.
Right.
T lambda acts on these. Right, so if you look at G, they commute with the dilogarithm part, but they don't commute with the gamma part. And the gamma part translates I said, by T lambda. So if you look at what happens to these variables under this adjoint action, they become these variables. There's the exchange. And that's the exchange. So for example, I said this is what happens, because I did mutate here, but I did this exchange of variables. So A sub A becomes A sub A. So at least it's reasonable. So if you're not used to working with quantum positors, maybe you want to ask why this particular form, but this is a recipe that we're going to take today. How these things actually can. This is due to you, it's actually. Okay, so I'm going to call something a q-Whittaker transform because I'm not an analyst. I work with the algebraic form of the q-Whittaker transform, which is just basically the eigenvalue equation. So the q-Whittaker transform of an operator on the quantum torus, let's say T lambda, is given by how it acts on this universal function, this universal q-Whittaker function. So for example, I said that G acts on this universal function by multiplying it by gamma of x, the Gaussian of x. So therefore, the q-Whittaker function of G is just gamma of x, which is the word missing there. So, and let's say the q-Whittaker transform of the Hamiltonian would be E of x, the elementary symmetric function of x. It's just the eigenvalue. So this is an element in the quantum torus. And the theorem is that its q-Whittaker function is the Royce-Nar's operator, the sort of leftover of the McDonald operator. It's going to be infinity of the McDonald operator. So these variables either can be realized in the quantum torus T lambda, or they can be realized in another quantum torus, T sub x, but they're much more complicated. There's these rational difference operators. And this is because we know what the eigenvalue equation is for the Royce-Nar's operator acting on the q-Whittaker function. So this is you just read the eigenvalue equation written on the left is on the right and the right is on the. And then because the Whittaker transform of G is gamma of x, and I said that A of A prime is just the adjoint action of C on A. Then I have some variables dA1, and they're going to be the q-Whittaker function, the transform of the other cluster variables, the A primes. And they're, because when you do a q-Whittaker transform, the order of multiplication reverses, then it's just the adjoint action of gamma inverse of x on the Royce-Nar's operator. So this is some complicated, well, not so complicated. I write it down explicitly q difference operator in x. And actually it looks just like the Royce-Nar's operator, except that the t here is multiplied by x. The action is very simple. The action of gamma of x commutes with this rational function. The only thing it doesn't commute with is ts.
And these double dots are in some kind of normal order.
Right. The double dots are, I guess, the strictly correct term is q-Weil ordering. Right? So it's a commutative product. I've seen them called commutative monomials, but I kind of know what it is. Okay. So if there wasn't an x here, this would just be the t going to infinity limit from the McDonald operator. Okay, so my claim is that I can compute the q-Whittaker polynomials. So that is, I said that I had a universal function, universal solution to either the system of Royce-Nar's operators or the Hamiltonian equation. And then it truncates when I choose values of lambda, which are dominant integral, into a polynomial in x. And that polynomial, well, it's just the product of this dA1s acting on the one. So the q-Whittaker transform of the A primes. And the reason is because both the A's and the A primes are cluster A variables in the same cluster. So they must Q commute. And their Q commutation relation is to Q them by meaning like this. So if I act on such a function with the Rissener's operator, well, it just Q commutes with this factor. So I'm going to get some eigenvalue equation. Because I know how the Rissener's operator acts on one, and I know how it commutes with these. I'm just going to get some power in Q. And so therefore, this is an eigenfunction, and I know precisely what the eigenvalue is. And the eigenvalue is such that it's got lambda is just the sum of the omega A and A. And this eigenfunction is unique, so therefore it must be this, up to some power of Q. So I've said this, I made this statement many years ago. I'm looking at it in a different way today, but when I made it many years ago, for those of you who are interested in some such things, the other cluster variables in this cluster algebra, when you use it into several times, you get raising operators. You don't get q-Whittaker functions, you get some characters of something called fusion product or gradient tensor products. And as we remarked before, this construction worked for any type grid system. You just need to correct quiver. To start with, you'll get some eigenfunction of some Hamiltonian, which is Toda-like. So Toda with a boundary. Okay, so I have a way of producing q-Whittaker polynomials, not functions, not the universal series, but polynomials, by a very simple action associated with a cluster algebra that I called the Toda quiver. So my claim is that there is another cluster algebra in here, and that's the new result. But the Toda quiver, I call it the Q system quiver. What that means is that classically the solutions to this cluster algebra, A variables, they're just short functions essentially. Or if you act with dA k on one, it's a short function of a k algebra. So the classical evaluation for characters of the k algebra. So, but actually, the characters of K modules are Q characters. They're starting around polynomial in commuting sets, which is called YIA. So you have an infinite number of them. For any value of A, you have n-1 values of I, including type K. Okay, Q characters, there are not going to be any Qs in the Q characters here. But I'm going to obviously quantize them so that I have quantum parameters. And the Q in Q characters is not my Q today. The T in the T characters is my Q today. So as I think you said that too many T's. Okay, so I just want to briefly flash the cluster algebra that appears here. Anyway, so Q characters are just norm polynomials instead of in variables xi over xj, some norm polynomials in the y IA. So for example, I give the two fundamental characters of SL3 here. And how you should look at this is that if you forget the variable A, which I call the spectral parameter, you just get the classical evaluation of the two characters of SL3, the two fundamental characters of SL3. So the classical evaluation is that YIA bar, this classical evaluation, is x to the omega I. So accepting this, there is a cluster algebra introduced by Hernandez-Leclerc, which I'm going to massage a little bit, because I'm only interested in the fundamental characters for the purpose of this talk. I'm going to write such a quiver. It's a triangular quiver, which will replace my toric quiver, which is the Q system. And I'm going to introduce some coefficients, and I actually explicitly give the initial. These are the initial x variables, not the initial a variables. So that's why I call them x. the alphabet here is very bad because in the literature, in the q-character literature, these are called K's, but they're not A variables, they're X variables. So, okay, I'll just write them down explicitly for SL4, all right? So, for SL4, I take the lowest weights, y10, y21, y32 inverse, and put them in as coefficients. And then I have these X variables, which I labeled. The first label is the thinking label. And the second label has something to do with the spectral parameter, the second variable, A. The initial X variables, if you look at them, they look like roots. Okay? So yi minus 1, yi plus 1 is just like yi squared when you do the e to the 2, x to the 2 omega I, and then the denominator of the two neighboring columns. So this looks like a root. And so I'll call it an L root. The X variables are L roots. And then I do the following mutation sequence. Okay, just watch my finger, don't read what I wrote. You start here, then you can do this one, then these three, then you go back. This one, and this one, you stop. And you go back and do this one. So you did this one 3 times, these twice, these once. And what will happen is you'll get this word. And yeah. What you see at the top is that the coefficient variables are, well, they switched around. You have omega naught in their connectivity. But what you have here, what I call chi32, chi23, chi14, those are fundamental characters. I mean, these are just the A variables that keep it out. They're easy to confuse. So I claim that after this particular mutation sequence, which is a truncation of sort of the Hernandez-Leclerc formulation, you'll get the fundamental characters. So if you put in this initial data, this is what you have. So after the mutation sequence, chi-IA is the fundamental Q character. So that is the character which under classical evaluation evaluates to the character of the omega I, right? Which is highest weight. So some recipe for getting them from the cluster algebra. And why am I mentioning this? This is a cluster algebra, so it has a quantization. The y variables were commuting variables. Obviously, I can make things into non-commuting variables. There's a q commutation between these x variables, therefore there's a q commutation between the a variables. So, and so forth. Only the literature on Qt characters uses t for the quantization parameter, and I want the talk to not have too many t's in it, so I change that t to a q. These are not QQ characters. That's another thing. But for me today, they're going to the L weights are going to Q commute. So, but if you quantize this cluster algebra, it's a theorem of Hernandez-Leclerc, and I think also Bittman, that the quantization of this cluster algebra gives Nakajima Qt characters, which are characters which don't necessarily commute, but they Q commute. These variables y note from non-commuting. When I'm computing, I just sort of renormalize fundamental characters because for Nakajima they don't actually commute, strictly speaking, but I renormalize them so that they actually commute. And but what doesn't commute is that there are some of monomials, Laurent monomials in these y's, these non-commuting y's, and the different terms don't commute with each other. So what I can do, so I claim these, okay. If I raise the Qt character to some power, and then so I can write this as the monomials, I have to multiply all monomials in all these Qt characters. When I multiply monomials, I'm going to get some power in Q, because these monomials don't commute with themselves. My claim is that if I have, that I have a certain recipe, which I'll call evaluation, I write it as a matrix element, but it's just an action. I'm going to get some sort of classical character out of this with some powers of Q after I do this evaluation. And my claim is that this is going to be exactly if I write down the correct definition of evaluation, this is going to be the q-Whittaker function. So how do I do this? Each fundamental character is just a lowest weight times a polynomial on the x's. Then I can write it this way. And Nakajima showed that the QT character of the product of fundamental modules is just this non-commutative product of characters. And then, okay, he modified this a little bit, and I will not get into how he modified this, but each monomial in here gets an extra power of Q, depending on how you have the monomial. And I claim if you take in sort of modified characters, this character is power invariant, and this modified character is not, it's a polynomial inverse. Oops, there's a T that escaped my notice here. This T is a Q. Okay, if I take a monomial that has some power of Q and do the evaluation I talked about, then I just get the classical weight times some power of it's Q, which is with T, which is a Q. Okay. So this is well defined. So I call this spectral ordering. This modified character of the product gives you, in fact, this q-Whittaker function. So I have two cluster algebras, one for which is sort of classical characters, and the other one gives this is QT characters, both quantized, and both act as raising operators for q-Whittaker function. To prove this statement, it's very non-trivial. I proved to you the statement that the Q-system solutions are eigenfunctions of the Hamiltonian, but to prove that this is going to be an eigenfunction of the Hamiltonian is very non-trivial, very combinatorial. Okay, I have how much time?
That was 7 minutes.
Okay, 7 minutes is something else new. So I said that I would eventually get towards the conjecture that we're trying to work on. So first, I have to affinize everything. So you can sort of see how I would close the Q system. I would just take the affiniting system and write down the quiver corresponding to this. So I just give you the X vector. So the only thing which is different from the original, forget about the coefficients, is I close, this is just rotational invariant. And the notation here is that I get a new variable P and a new variable kappa. Just a notation. So I call the affine weights. So something like e to the x to the delta is P inverse, and then T gives you a kappa. So these two variables are actually P kappa delta. This is because this is the standard nomenclature in this Person's function business. And then you can think about what the affine dent twist would be again. I can just mutate with all these variables and switch. Right? It's the same recipe. And I'll get it's a quiver homomorphism. It's realized by the action of now what I call G hat. And G hat is almost the same as G. Only there's an alpha 0 here, n is equal to 0. Okay. So there's one more dilogarithm because I have one more node here. And also gamma is no longer gamma, it's gamma hat. Because here I should be able to translate P or e to the delta. And the action of gamma hat on my quantum torus is the same as before, except for on P, which is now part of the quantum torus, translates it by the variable kappa. So you can do this with a root system, but this is sort of the standard notation. So it's a slightly larger quantum torus. But the key here is that this G operator, it does not commute with the Hamiltonian that you compute for this system, which is the closed Toda Hamiltonian. The closed Toda Hamiltonian is slightly more symmetric than the open Toda Hamiltonian. It has this P term here, a term proportional to P is equal to 0, you'll get the open Toda Hamiltonian. So finite P, this is just a Toda Hamiltonian on a closed chain. And G, it's like a dynamical symmetry. If you act with G, the adjoint action with G on H translates P by K. Because of this back together. So we don't really look for eigenfunctions of H. Well, we look for eigenfunctions of G hat. That's the advantage of considering the standard operator. So up to some normalization, they're going to be again an expansion of q to the minus lambda positive roots, which includes kappa as a variable. Instead of looking for eigenfunctions of G, you can look for eigenfunctions again of this renormalized G. It's just some adjoint action on G. And you look for solutions to the eigenvalue equation. F is 1 plus something. So T acting on F is F. Solutions of as expansions in Q to the lambda to the negative roots, which starts with 1. And because G doesn't commute with the Hamiltonian, these are called non-stationary states. They're not eigenstates of the Hamiltonian. The eigenstates of G or T. So this T operator was written down before in a more general form for the Reisner's, the elliptic Reisner's case. So that's the picture. So looking for solutions to such an equation, there's more variables in elliptic Reisner's. I mean, there's T in elliptic Reisner's. But everything is conjectural for that case. This is the reduction T going to infinity of their operator. So for closed Toda. And we can prove some things. For example, this equation does have a unique solution up to normalization. And that analog of q-Whittaker polynomials, for example, that's no longer a polynomial. We don't expect polynomials. This is an affine system. It's going to be a series in kappa. So you take affine dominant both ways. And what comes in here is qn minus lambda n. It's not just an integer, but it's an integer plus log p. So p somehow comes into this restriction. And we call these evaluations of these dominant integral affine lambda the analog of the q-Whittaker polynomial. It's their series. And the claim is, so the reason I introduced this T character cluster algebra is the following claim. So I'm just making claims. These have proofs. My collaborators here are Berstein, Jean, DeFrancesco, Pasquier, and Sherry Sheets. For you to be connecting people as we go along. Okay, so we have raising operators up to this bosonic character. We have raising operators for what's known as affine normal functions by some people. Which are these S's. I called them D's before, now I call them S's. And they also have an interpretation as QT characters. But they're QT characters for certain infinite dimensional modules for the quantum toroidal algebra, which I'm not going to discuss here, but it's some limit. The GLN quantum toroidal algebra, and the modules are the Fock modules, so there are n of them. And so I'm going to have NSIs. And there is a combinatorial method of computing these QT characters. I don't know where it appears in the math literature, but it appears in the physics literature. And this evaluation here is analogous to Nakajima's solution. Do I have 2 minutes?
1 minute.
1 minute. So it's analogous to the Nakajima spectral ordering. Okay. This is the quiver associated with these characters. But the sequence of mutations now is very different. It's not the Hernandez-Leclerc sequence. If you just look at these coefficients, you do a sequence of mutations, which I don't have time to explain. It goes all the way down to minus infinity. And you'll get this affine QT characteristics. Okay, I won't get into this because I only have 1 minute. Okay, so I'll summarize. So for the open Toda, I introduced 2 quivers, the Q system quiver and the P system quiver, or the Hernandez-Leclerc quiver. And I said I can get raising operators from either of those. I don't know the analogous statement for the Q system quiver. I showed you the Q system quiver. I got my Hamiltonian and my then twist operator out of that quiver, but I don't know about the raising operators. I don't know about the solutions to this. Although I believe there are some papers that suggest like that should be, but I can't get those from the some sort of generalization of the Hernandez-Leclerc. And then the conjecture of Shiraishi, Langman, Nomi is, well, they wrote down the actual eigenfunction, the universal series for the elliptic Burson-Myers model conjecture. And they conjectured there were eigenfunctions of T, that there were unique solutions, and all kinds of properties of these things. And so the purpose of this project is somehow to work us up to this. As soon as you T deform, the cluster interpretation becomes very non-trivial. But at least in the q-Whittaker limit, it's nice. So thank you very much.
Students.
What was the role of the red arrows in the quiver?
Oh, no, it's because it became too messy. I just wanted to show that I put this on a cylinder. I take that Hernandez-Leclerc thing and I close it up this way. Yeah. Yeah.
So you know the walk of XA body.
Yeah. Yeah.
They write all those
Yeah.
operators
Yeah.
for equations. Did you try this? And did you?
I didn't go into any of the combinatorics, but I think that their model is related to the combinatorics of these affine characters, yes.
We keep some, for instance, you know, when you said when you rescale, you lose the symmetry. If you use their forms, maybe.
You mean from the symmetry is when I go from McDonald theory to q-Whittaker theory.
There is not.
So they have q-Whittaker and they have McDonald. But in this particular approach, I'm only looking at the cluster algebra content. So, or the combinatorics, and the combinatorics that has to do with this is for the q-Whittaker. And I actually don't know how to generalize the combinatorics yet. Yeah.
I have questions. So what knowledge of class algebra do you use actually?
I'm sorry,
So what kind of knowledge do you need to know about class algebra? So you need to know the notion of mutations.
Yeah.
And then what else? Do you need some deep properties?
So I only use the 2 things.
Yeah.
Well, I only use really 1 thing. I need to compute the Dan twist. That's 1 thing I use. In this talk, the only thing I used the quantization. That's what I got from Westra.
Yeah.
I didn't say anything about.
And Nakajima already know the quantization essentially.
Yeah, I think that Nakajima wrote down this quantization, and then the cluster algebra content was understood by Hernandez-Leclerc. And I'm just using in fact, I don't need to use the cluster algebra, right? I can use some other combinatorial tools to compute these things. So I'm just showing this content because I speak in this language. That's how I do the combinatorics. It all comes down to tableau combinatorics. I see. Because these are very simple characters. Yeah.
Just a naive question, let's say in the slide about the non-stationary state.
Yeah.
I mean, so, not just naive question is, I mean, also this Imagine some kind of stationary states as well.
Yeah, so that would happen if in the limit, when kappa goes to one. Kappa rescales p, and so if there was no kappa, I would have stationary state. This has an essential singularity. The eigenfunctions have an essential singularity. You would have to renormalize them, so you do a WKD approximation, and you'll get some stationary states, which are eigenstates if they're close to it. Yeah, but it's a delicate procedure to do that. And there are also many conjectured things about that. Yes. Yeah.
Look, this thing could be.